embarrass me. You know that. Right. Hello, everyone. My name is Amijai. Some people find it hard to pronounce, so you can vary on the name or just go with A or whatever you choose to call me. Um, Today, we're going to go through a 24-hour session of a protein design hackathon. I think it's the first one ever maybe, a general public protein design hackathon. But at least I will be brave enough to say that it's probably the first one in Europe for sure. The topic of the protein design hackathon is taste. So how can we use proteins to create different tastes? And perhaps I should start with kind of a general presentation and move slowly towards technical and what we're going to do. So uh, I guess most of you know what's all proteins. Um, so basically, they're nanomachines that and scaffolds and kind of structures that power life in general. Each of our cells has tens of thousands. Well, depends if you count the types or the number, but a lot of each one of these proteins. These proteins, for example, here, these membrane proteins are responsible for generating energy for. Oh, sorry, those generating energy for our body. Here you see like structural proteins that kind of shape the cells. You can see here a walker, literally a robot that goes on the scaffolds inside the cells, and the entire machinery that is responsible for replicating and maintaining the information. That's kind of the hard drive of our cells, right? And this is natural protein. This has nothing to do with protein design. This is how protein behave and evolved during the 4 billion years that life evolved, right? And but okay, so here we see shapes, but all these shapes is just a sequence. So what they are is like each of those proteins is composed of a very long chain, starting normally from methionine, which is one building block, and it's made of like different building block, which kind of form a long chain. It can be like 1,000 and even more building block long. And each of these letters represent a different chemical group that is attached to the basic Lego brick that compose this chain. And because these chemical side groups have different properties, the chain will fold into a specific structure. Now, this is how, when we are looking for a sequence in a database, this is how we will see it, right? So we'll just see a sequence of letter. Each letter is representing a different amino acids, which are the building blocks of protein. And this is basically a protein that goes into a specific place in the cell. It folds into the membrane, and then it transports ATP in exchange to ADP, which are kind of the batteries of the cell. And the nice thing that it's actually translated from DNA. So this chain of amino acid is encoded in this code. Each codon of 3 nucleotide represents one basically unit in the protein. And this is actually quite cool, because it means that if we have a sequence of a protein, then we can take the DNA of this protein and just throw it into, hopefully, yeast and not bacteria. Depends who you ask, but you can throw it into algae or into bacteria or yeast and generate a lot of it. So basically, we don't need to. We have these amazing fine structures. Let's go back up. We have all these structures, and we can do a lot more. And all we need to create these are nanometer size. All we need to create them is to understand what is a code that makes them. So we don't really need to create this shape. We just need the sequence. So wouldn't it be amazing if we had this kind of formula that will link this sequence to the structure? Then we will be able to, first of all, if we get a sequence, we will immediately know what the shape is, and then maybe even cooler, if you want a shape, we just give the computer a shape and gets a sequence. So whatever shape we want to create, we just get a sequence and express it in bacteria, let's say. So that will be amazing. That's a whole new branch of technology, right? So if you want to formulate it in a slightly more scientific way, you can put this into two problems. One is a protein folding problem that is just basically given a sequence of a protein, what will be the 3D structure. And the other problem I mentioned is the opposite problem, which sometimes referred to as a protein design problem, which is given a structure, predict one or more sequences that will fold into the structure. And this is a bit more complicated because actually you can have more than one sequence that generates this structure. So this will be really cool if we will have those, right? So in 2021, two breakthroughs happened in parallel. The truth is that, you know, this model was out and about a bit faster than this model that was created in our lab by mimicking. This was created by Google. And basically, these models allow us to give them a sequence and get a structure from the other side. And they are pretty fast, so you can take 10,000 sequences and get a structure. Well, depends how many GPUs are available, but you get the structure the next day, which is kind of cool because now maybe we can design stuff and very quickly check if they are folding to the structure we want them. So this is kind of amazing, and this kind of the breakthrough of 2021 in science and in Nature, the two, I don't know, at least the most hyped magazines in science, and but it didn't stop there. So this is actually from the beginning of January. It was the diffusion. I don't know. Okay, so this is kind of beginning of January, end of December. The latest models, it's not even published, it's like published in bioRxiv. It's using a design model that basically you kind of give some restriction to the model and it will, like magic, create the shape for you, so you can see how the model is kind of searching for something to, like a shape to optimize to, and actually it starts here and then it ends like this. It's kind of the other way around. So the New York Times got it a bit wrong, but basically you can create very quickly diversity of shapes that will be defined by restrictions that you give those shapes. For example, you can give the model a restriction. I want a certain building block in exact distance from another building block in my proteins. Okay, or you can say I want it in a certain symmetry. I want it in a C3 or a C2, which is just a different relationship between your monomers, and the model will automatically generate it for you. And to make like a modest-sized protein with this model, for example, will take I don't know, depends how big it is, but I think 10 minutes you will get a protein. Some other designs methods will give you a protein even in 20 seconds. Depends what the inputs and the output that you are asking from. So, you know, this is the latest design model, but we also have other design models. There are two published models that do hallucination, which is basically taking the computer and tell them, okay, given all your knowledge about proteins, generate a new protein. And it will start to, not exactly randomly, but start searching in in a kind of based on an algorithm. It will start searching the sequence space until it will find something that will fall to something he understands as a protein, and then you can start putting restrictions and get some things that you like and generate a lot of structures that are kind of hold properties that you need. There are also autocomplete models that you can use to take a part of a protein. So let's say that we take a part of interesting protein from nature that we really like, perhaps something that bind a rare earth metal to clean water from ions, or part of a toxin of a bacteria. And we want to give it other properties by generating, auto-completing another protein from this. So we have also designed models that do, it's called in painting. So we give it kind of a part of a protein and it will auto-complete the rest. So we have a lot of diversity of things. Many of them are now for free, open source, online. You can just go and plug into Google Colab and just find the resources, and many of the resources will be given to you today. And you just start working with them. And given enough GPUs, you can quite quickly reach a protein that will actually fall to something that you know the structure from the computer, which is pretty cool, because then you can just buy very cheaply a DNA and you have the protein you designed on your computer a few days ago. So this kind of reminds this. Do you know them? So this is how Google started. And I think biology for most of us is something done in labs, and you need very expensive equipment. Normally we are associated with medical solutions. So you need, 5-10 years FDA approval, and things are very expensive, and you need spatialists and so on and so on. And now with all these models, where all we need is a laptop and a few GPUs that you will have today, you can sit down and design a protein that could have amazing properties. And we will see at least one interesting property that we can design for. Right. So let's be more specific and start talking about what we're going to do today. So shades of taste. So we know to make colors, right? It's pretty easy to make colors. This place is pretty colorful. We kind of control colors in a nice way, but we're not very good in making taste. Honestly, we're not very good in making smells as well. And if we design taste, for example, Coca-Cola, it normally is not so healthy. Now, another thing I learned is that even putting aside the health effect, and I think you're all familiar with things like diabetes, obesity, and dental problem. I hope you're not familiar with, but most people think 98% of the world population will experience at some point some kind of dental problems. So sugar is a problem. Now, when I researched into this, I discovered also that sugar is a problem also in terms of sustainability. So actually, perhaps a bigger problem. So there are calculations from the different foundations that try to understand how much water you need to make one can of soda, of like sweet Coca-Cola, and not the one with the Pepsi Max or whatever. So apparently, someone calculated that you need 200 liters of water to make one can of Coca-Cola, which for me, using so much water to just make the sugar is incredibly inefficient if I can put a microgram of protein and give you the same sensation. So perhaps we can design proteins that will bind different receptors in our mouth and give us diversity of taste, right? And this is where we get to challenge number 1. Right, so this is the sweet taste receptor. You will all have it on your computers tonight, so don't worry about the details here. This is actually a heterodimer, which actually means that these two proteins are different. They come together and form a huge diversity of taste. So different molecules that will bind the receptors into these pockets. This sits here. There is a membrane here. Will induce different sensation of taste. Actually, it's enough to change a bit the water composition of these receptors, and you will feel different taste. So somehow this receptor, so the same set of two proteins, and there are other taste receptors that give us different sensation. But even if we consider only this receptor, you can create a huge diversity of taste just with this receptor by interacting with it in different ways. Now, if I will tell you now, design a taste protein from scratch, you will have a problem because you have no idea how to start working with this receptor. I mean, that's pretty hard to know how to tackle this. Lucky us, nature created several proteins that give sensation of sweet. So these proteins are doing exactly the job. They bind into the receptor, and this protein will actually give a sensation that is 80 times stronger than sugar. So, you know, this in your coffee will give you, well, I don't know if it will be stable, but this in your soft drink will give you a sensation of incredibly sweet drink, although you will be just eating proteins. So it could be just water with this protein. So then we have a question here that maybe we don't, but at least this might raise a question where, well, if nature is doing it, why do we need to engineer proteins to do the same thing? We have them. Let's just take the sequence, produce them, and replace sugar. So the reason why protein design allow us to kind of do something much better is that this protein might be unstable, very hard to produce. So a lot of native proteins, you cannot produce them in large quantities. Some of them will not produce at all in E. coli. So you need to kind of find sophisticated ways to produce. And this is not, you cannot leverage it. You cannot make it a solution, even not a niche solution to anything. Where using protein design, you can capture the essence, the region in the protein that interacts with the receptor, and then cut the rest of the protein, for example, and this will be just one strategy, and create different shells that hold this. Some of them will be much more stable. You can boil them, you can leave it on your table for a year, and they will still be good. While these proteins, I don't know any of them specifically. I never worked with them, but a lot of native proteins will just break if you leave them on your table. For example, antibodies that are used and given in hospitals are very unstable. You need to keep them in frigidators. And I think you all remember the COVID vaccine, which was RNA, right? But still, biomolecule, we had to keep them in -80. And this is the case, for example, for many cytokines and other classes of proteins. So by designing these proteins to have properties of stability, for example, or different lengths or thermal stability, we can create a protein that could now be generated in kilos or maybe tons in algae, and perhaps start thinking about creating sustainable sugar, which is not really sugar, or sustainable taste. Another thing is that we can diversify the taste just by perhaps changing something here, or even changing the other sites could generate, like the periphery of the protein can generate other taste sensation, the same way that I showed you before, that one molecule will produce a certain sensation of taste with the same receptor, and another one will arouse another sensation of taste. We also have other proteins that, in my opinion, are cooler. These proteins actually switch the sensation. So the one here in blue will make you feel like I don't remember which is which, but the one here in blue will make you feel like sour things are actually sweet. So if you eat sweet and sour chicken, it will be only sweet. You will lose a sour sensation and replace it with sweet. The other one here will make the opposite effect. So not only that you can create a protein that will induce a sensation, you can create a protein that will switch a sensation that is induced by things we normally eat. So yeah, so the idea in the first challenge is to work, and this is more application of existing script, using existing scripts that will be available for you and the literature to try to design a protein that will interact with a receptor in an interesting way. And you can actually test it later on with AlphaFold, which is one of the models, and see if the proteins that you're designed actually kind of docks into the how it interact with the receptor in comparison to the native protein. So you can test it to see how you change the properties of the protein. So that's challenge number 1. The challenge number 2, and this is really, I didn't know what will be the final composition of people in the hackathon, so you don't have to do challenge number 2 or you don't have to do challenge 1. It's really what attracts you more. If you're more computational, perhaps you will be more interested in challenge 2. So here it's a different question. So as you can see, and here we're looking at kind of in gray you see the protein I showed you before, the receptor, and here in red, maybe you know this molecule, it's kind of surrounding us, it's water. So water play an important role in, or more correctly, organized water in receptors and in proteins in general plays an important role in the way protein interact with other molecules. Now, unfortunately, right now, when we predict a protein, we don't have explicit positioning of water molecules. There was an attempt to put other molecules like ions and different ligands after you fold the protein, but we don't know how the water organized around those proteins. So the idea here, and maybe I can show you something a bit more interesting than this static picture. So, right. So here is a receptor, and you can really see, and here to this receptor, sweet taste receptor, there is a molecule in the middle that stimulates it. It's called glycine. It's actually one of the building blocks of protein, but here it serves as a kind of ligand for the receptor. But you can see also how the water molecules are surrounding it and in a very specific way inside the receptor. So it's not only outside, and this cannot be predicted. So this is experimental structure, but if I will fold this, I will not know how the water is there. Luckily, if we go to the PDB, we'll find a huge database of proteins with water molecules. So it's possible to start thinking about training and building a model that will know to, given a structure, to position water molecules, at least in places where it's there is some sort of enclosure that it's more kind of, you have better option to predict the position of the water. So the challenge number 2 is not about using existing wait, I need to find the presentation. Right, so if you're interested in purely coding and using databases to kind of build the new models that will be useful. This is, by the way, an unsolved problem, and just to work with the databases, to get familiar, to see how you can start working with this model. This will be the challenge that you might choose. Right. So now we're moving to a more technical side of the hackathon, and basically how this is going to work. So first of all, we're going to work in teams. The teams will be 4 to 5 people. We need to see, maybe there will be a team of 3, but the idea here is to combine skills. So you don't want a team of computational people, a team of scientists, a team of biologists, and so on. You want to mix, and we will have like a form to make sure that people are together in the right combination. This is really important because you will have also to divide the task between you. Make sure you are choosing the same challenge. If you have a spatial challenge out of the 2 challenges that you want to pick, perhaps you kind of want to make sure you are going to agree that everyone want to use the same challenge. Each team will have an administrator. The role of the administrator is simply to hold the account that will have the GPU. The way we'll do it, Colab offers GPU time. It costs money. We will pay for it, but then we cannot go with our credit card to each account and put our credit card. So the way we will do that is that the administrator in the group will put his details, and then he can submit it to Mikhail, and then get refunded for, this is 10 euro, I think, for 100 hours, which will be more than enough. And we get refunded directly for the cost of the GPUs. Now, this will be later because we will not get to submitting so quickly. But basically, the way it will work is that everyone has access to GPU, but it's very weak. This is the business model. So you can run stuff, but then you cannot run 1,000 designs or even 50 designs. It will be slow, so everyone can play with us, but when you actually want to submit something and check a lot of designs, and you will need to use you kind of share the collab to the administrator, and he will send it. So it's a good thing if your administrator is also the kind of the more experienced guy in coding in your subgroup. Right. Hardware and software. So you saw me playing around with PyMol instructions on the cheat sheet, how to install it on your computer. I think it's free for Apple and Linux. I don't know how many of you are using Linux, Ubuntu, for example, but then it's free. For Windows, you have a trial period, and if you're a student, you can download it for free. I think that you just need to go and put like your email and some details, and you get like the free version for a student. So you can ask me when you start doing this. GPU time. You email your the administrator, email the collab receipt to Mikhail, and receive a refund. You also need to email some way for us to send you the money. So I think he's using Swish. But there are details in here, and if you have a problem with this, talk to me. I will solve it. Right? If you are using something from Git, then install the packages and dependencies. Just make sure you have all the dependencies, because otherwise script tend not to run. And you will have a lot of details, like I said, here in the cheat sheet, that also give you a link to the 3 workshops that were here with all the details about how data file is structured and so on. And I'm here all night to answer questions, right? So that's my job tonight. Yeah, I kind of predicted the next slide. Right, advice. So first of all, at least in the beginning, I will try just to run around. But if you have a question, just put your hands up. I don't know how it will be, or just call my name or something, and I will come. Another thing that I advise you to sit down and think carefully how you're going to kind of tackle the challenge, and then when you come with a strategy, sit down with me for 15 minutes to get some feedback to make sure you're going for something reasonable and that the design process makes sense and it's not like protein design is hard. So just to make sure that you kind of took a reasonable approach for the night. Okay, so tips. Divide the task in the group. Make sure that someone is doing the literature review, going, for example, into the receptors and checking the papers. If you have problem to access a paper, let me know. I will download it and send it to you. I don't have the pay. Well, I think also other people here have access to university resources. So yeah, just ask around. Some people will get you the paper, even if it's after like a paywall. Someone will have to do coding or at least play with the existing scripts. So that's another person. And then finally there will be testing. So this is not exactly coding. It's probably someone else that need to take it, fold it with AlphaFold, maybe dock it to the receptor. So try to divide the roles between you, because if everyone is doing everything, it's going to move slowly, and obviously based on expertise. Before you jump, I mean, obviously you will probably start with playing, just getting the scripts and doing the technical stuff. But before you jump into designing, sit down together, devise a strategy. Based on this strategy, I could also start you up, tell you like, okay, this is probably this is probably the scripts you need. And if you will have questions that are specific to this kind of strategy, then I will sit down with you and give you more details. But first, before jumping to actually working, and I'm not talking about playing around with the script a bit, um, to the actual work, submitting things to the GPU, think carefully about how you're going to approach it. And then finally, keep things simple. Protein design is really hard. I mean, if we will be here, three or four people, well, three or four people from our lab, and we will need to design all night a protein that will make an effect, we will find it hard. I mean, we'll probably design something. I don't know how well it will be. So take it as a learning experience. In the end of the evening, you might have something that might work, at least on the computer. I don't know if it will express or not or thing, but you will learn a lot about how to go about it. How can you, in your, I don't know if people sit in the garage here because everyone is going on train, but how can you, on your sofa at home, design a protein, or in university or so on. Right. It's around 2 o'clock tomorrow for you, those of you who are going to survive. There will be two things. First of all, I will ask everyone, all the teams, to start organizing and making presentations that will show in 15 minutes, more or less, what they did. So, what was the challenge they decided to tackle, what was a strategy, how they implemented it, issues, mistakes, and results.
Yeah, thank you, everybody. It was really nice to have you here over this hackathon, which Amijai was so kind to get for us. So we have a special award I will give Amijai. It's a golden sticker, which is quite rare. So, so we normally these stickers comes in white. Yep, but this one is
It's a
golden.
collection.
It's a collection.
Collector stuff.
So you have to have it on your laptop to show off to people. So, oh, you have a golden sticker.
Thank you very much, Cal.
For
I will put it in a spatial place, I promise.
And we will have some presentations. And first, Amijai would like to say a few words.
Yeah, I just need to put the collectible item in a spatial place, you know.
Ooh.
Right. So, right. First of all, really thank you. I just pretended I'm doing stuff. I didn't do a lot. You guys did the work. I just answered a few questions. I am very tired, but I really enjoyed it. And my perspective on it, I really believe that protein design has a potential. This is a word disruption, which also that many people see it as an opportunity to make money. But for me, it's more about changing the way we manufacture things. We do lots of things that, for me, are not sustainable. And maybe some of you see me, I don't see myself as an expert, but maybe some of you see me as an expert. But I think as a person that goes to organizations, either a university, a lab, or a company, I'm not really able to make an impact. So if I will be extremely charismatic, I will get the manager kind of excited for 25 minutes, but I'm not really able to sustain excitement about new technology. And people in general are very conservative about the way they do things. So for me, it's a great pleasure. If you enjoyed it, I hope you enjoyed it, and it took in a lot, and you would like to do more of this. And that's, for me, means that you will nag your organization, if it's a lab or a company, that, guys, we need to start thinking about that. And if there will be enough of you, there will be enough companies and organizations that will start shifting towards using protein design as a tool to kind of manufacture. And this, for me, it's a great pleasure. Besides the fact that I had a lot of fun, it was really great. I might want some sleep now, but it was really great, and thank you very much. And hopefully, yeah, you will have a presentation. And let me know if you keep on working on this and you want to get more feedback. Just email me, share the slide, share the code. I can still give feedback even though I'm on the other side of the planet for some time.
Okay. So yeah, our aim was, after some discussions and literature research, to improve a protein called brassine. So a little bit of background to that. Do you wanna?
One of the reasons, okay, thank you. One of the reasons why we picked this protein after selecting some of the others that were candidated earlier last night, some other search, was that we found that it's one of those that are a pet sweetener among any researcher, for the reason that it is very heat stable, which is a really important characteristic when you want to design something that goes into food. So here's the structure of this sweet protein. I think it's found, was a plant again. It's in West Africa, where they have been classically sort of extracted to find those and identify them. So it goes to the next slide, please. So on the receptor side, we found an interesting article that described where brassine, compared to some other sweeteners, classical sweeteners like cyclamate and lactosol, where they are acting. So we find that brassine actually then interacts with two different spots, and this being then the membrane side, and this is then the sort of receptor side that we saw in the picture from yesterday. And our workflow then a little bit, of course, started with research, the literature, find quite a lot of people that had pinpointed the exact amino acid that were relevant. Fortunately, they do not always agree which ones are the most important. But we ended up having then a selection of saying, fine, let's go with brassine, and then go further with that in terms of we run it into the MP and NN. And then that output gave us a variation of sequences. And then bit by bit, as we learned from the literature, we started isolating and locking down. And say between those three, we started creating variations between those. Unfortunately, all of those three were kind of on different sides of this very small molecule. That is kind of a trick, because it indicates, for us at least, that then this is kind of tightly bound into the receptors.
Yes. So, did you get to that point? Yeah. Okay. So that was the first step in our workflow, and here you can see an example of one of the variants that came out of the MPNN, and then we folded it with ASM fold and aligned it to the native brassine to just verify that the important regions are not completely different. And then we continued with the workflow by we fed it into AlphaFold, the output from MPNN, and then picked some that had a high confidence score. So we just set an arbitrary cutoff of 0.8. And then we wanted to define a window of critical residues that we knew from literature were really important for the function and the binding to the receptor. So we don't want to vary those, but we wanted to vary the rest of the structure just to give it more variation with potentially new, improved characteristics. So yeah, we went back to the literature. We looked for important residues and found some, like this D29 residue, that if it was mutated to lysine, it is much higher in sweetness. And there was another residue that we didn't want to touch because it was shown to lower the sweetness if it's mutated. So that was a good indication. And we also identified some other high and low risk windows for restrictions that we wanted to try out just to see if it would, if it would give us different variants in the structure. So again, a little example of our output, which we got from one window that we designed, or that we've picked, which was from these residues that we wanted to keep constant, and the rest should be open to variation by the algorithm. And again, we aligned it to the native protein to verify that some of the important regions are not changed too much. You want to continue?
If I can cover this one. Yeah, so the steps further then is to elaborate that these locked ones, we also have a sort of a doubling of the amount, since we could change the amino acid 39. We could then go through, check the sort of alignment here, but then we decided we need to keep this N-terminus stable, because that's one of those that we knew that that's one, if that is modified, it will reduce the sweetness. So we want to lock that down. That gave us then the indication that when we're now going into imprinting, we need to sort of extend the chain in the other end. So therefore we have this extension here, and 5 to 50 amino acids, and then we're locking down everything in this 1 to 54, which is practically the native molecule. And we had 46 designs, so we came up with a couple of two selected candidates, which we then go out and confirm in AlphaFold and the ESM fold to see how do those structures that come out on the PDA, how do they actually fold. So we have a few pictures, I think, on the next slide where this folding is.
Yeah, so the next slide will be our last slide. But just to also say that this is not finished yet. Our aim was or would be to continue to diversify the chains and then have a selection process to find potential candidates that actually have increased sweetness. But because we had a very restricted time, we just picked, we followed up on a few candidates and a few variants. And this is just an example of some of the output of the final thing that we ran. So this was basically this N-terminus that we varied or added to the actual structure of the brazonin, and so you get quite different structures. So this was just to compare two of them that show quite different sequences and structures. So who knows if this will result in improved sweetness.
The next thing will be to guess do 10,000s of variations, and then
exactly.
That will make a meaningful as for dimers or some other functionality. But that's a lot of work to do. Thank you very much.
Thank you, thank you.
It's a PowerPoint karaoke.
Yeah. Welcome to the PowerPoint karaoke. So we worked together for many hours on two different things. One of them didn't work out, so we're gonna go into it right now. So, what is miraculin? So I'm not sure how many of you have done this maybe in school. At some point, a few years ago, miraculin got quite popular as something that you do in school science classes, where you pop one of those little pills in your mouth, and everything that's sour you taste afterwards, it would taste sweet. And that is immensely interesting because miraculin is a protein. And last night, when we were just coming up with different ideas, and at some point I just thought, why don't we work with miraculin and see what happens? And we started a bit of investigation on what it looks like. And during the process, we also learned a lot about how the proteins would bind with the taste receptors when it comes to sweetness and how it's related to bitterness. But mainly we looked at how miraculin worked and identified a few possible mechanisms. So first of all, it would change, it might change structure at a lower pH, and that might be the mechanism of its action. And that's why it was very complicated to work with, because in our system we couldn't have a way to visualize what a protein would look like at a different pH. So that's complication number one. But here we did manage to identify a few histidine. Histidine. But if you want to think.
One histidine and 2 arginines, or is it aspirin? Asparagines. And the histidine is important because it's probably the relevant residue for the pH sensitivity, and the asparagines, I always say it wrong, are glycosylated, so they bind to sugars, and these are then important for the structure and how it triggers the TSIR2 and 3 receptors.
Thank you. And another factor is that we pulled this thing out, and this is the top of the receptor that is supposed to bind with it. You took a look at that as well. And when you work with sweetness, this is basically the thing that you look at. And so we identified the possible binding sites, and the size didn't match up with the miraculin. So I guess at around 3 a.m. we decided to move on to a smaller and more digestible protein. And that is how we came to, well, this is a mechanism of action of the taste receptor. Really lively, actually. Yeah, didn't expect that. To monolin.
I can take over. Monolin is also a protein. It tastes very sweet, 8,000 times sweeter than sucrose. Very sweet, which means that you can have the same sweetness but with 8,000 times less of the protein, or the material. We chose this in a bit of a fit of a panic in the middle of the night, when we realized that all we have done so far was just not gonna work. And we chose it because it was smaller and it had Amijai's blessing. And it seemed easier to use. And as we investigated it further, it was evident that there was a higher consensus of what the active site was, and also the stability of the protein in general. This is how it looks in a very fast and jiggly movie.
Do it again.
And the goal was to create a library of potent monolin isomers that hopefully will retain the sweetness, but maybe change the characteristics of the sweet taste from it a little bit, and then to get 50 shades of taste. So the process that we tried to do this with was that first we identified the active residues, which are these that go snug into the receptor, and then we tried to look around them and see how much we guessed was important. The plan was to have a shading, a gradient of sizes that we decided to keep, and we would have had time for that had we only had a couple of more minutes. But in this case, we simply took the biggest structure that we decided was important, which is all in green, and everything in magenta we let alpha. We let in painting change and increase and in size. Then we took this in painting, chucked it into MPNN to get a whole bunch of more sequences that would have this structure, which we then folded in AlphaFold and took the literal output that said best. And this output is on the next slide, maybe? Look how good it is. It's the best.
But what is not shown here is all the work that Armin had done.
But I'm not sure what I've done. But now I kind of understand what we've done actually.
That's good. We have no idea. But we know that that this loop here is the same as if you go back. As this important loop here. It's not stabilized in the same manner, so maybe it will have a different kind of sweetness, probably for sure, or maybe it won't be sweet at all. Maybe it will even act as a sweet antagonist, so everything tastes bitter. And the rest, for some reason, did not fold super very properly.
It's just one of the many things that turned out.
Yeah. And there are good reasons for this that we understand and can improve for the next iteration. I will not name them.
To protect intellectual property.
Yes, of course, of course. Especially the investment of our investors as well. Yes. We run on pizza and coffee.
Thank you.
Thank you.